Statistics, Week 8, Part 3. Here's an example of calculating a confidence interval. So you should try this, pause the video, and then look at the answer. 8.1. Suppose we have data from a sample. The sample mean is 15 and the error bound for the mean is 3.2. What is the confidence interval estimate for this population mean? X bar will be 15 and our error bound measure is 3.2. The confidence interval is 15 minus 3.2, comma 15 plus 3.2, and calculating the values gives 11.8, comma 18.2. If the confidence interval level would be 95%, then we say that we estimate with 95% confidence that the true value of the population mean is between 11.8 and 8.2. To get a 90% confidence interval, we must include the central 90% of the probability of the normal distribution. If we include the central 90%, we leave out a total of alpha equals 10% in both tails, or 5% in each tail of the normal distribution. To capture the central 90%, we must go out 1.645 standard deviations on either side of the calculated sample mean. Now that 1.645 is something that we will actually compute. In fact, it is the z-score from a standard normal probability distribution that puts an area of 0.90 in the center and an area of 0.05 in the far left and an area of 0.05 in the far right tails. Our question is, how do we figure out what this error bound is for the confidence interval? And we'll do that next. We know that x bar is normally distributed. X bar is represented, the random variable represented by a normal distribution with mean mu of x and standard deviation sigma over the square root of n. That's the standard deviation that has been modified in the way that we do that with the central limit theorem in chapter 7, because we are working with samples and estimating values from an unknown population or population mean. When the population standard deviation sigma is known, we use a normal distribution to calculate the error bound. The steps to construct a confidence interval with unknown population mean and known standard deviation are as follows. The first thing we have to do is calculate the sample mean from the data. That you can use by using the list function, a TI calculator, or using a spreadsheet. Our first step that we'll compute is to find the z-score that corresponds to the confidence level. Our second step will be to calculate the error bound for the population mean. We will construct in the third step a confidence interval, and our fourth step is to explain what the confidence interval means in the context of the problem. Step number 1. Find the z-score for the selected confidence interval, whatever level you choose. You may want to go over this part several times to understand what's going on. The true fact of the matter is that once we compute our z-score for a given percentage, say 95% or 90%, you won't need to do that anymore, because that score will be true, that z-score will be true anytime we have a 90%, 95%, or whatever confidence interval. We can simply reuse the value. But it's important to understand the steps in the process. We need to find the value of z that puts an area equal to the confidence level in decimal form in the middle of the standard normal distribution, which is z is a random variable represented by the normal distribution with standard deviation 1 and mean 0. The confidence level, CL, is the area in the middle of the standard normal distribution. CL is equal to 1 minus alpha, so alpha is the area that is split equally between the two tails. There's a diagram that will come up in a minute and you'll understand that a little better. Each of the tails contains an area equal to alpha over 2. The z-score that has an area to the right of alpha over 2 is denoted by z of alpha over 2. So here is what we would get. If we knew our error bound measure, we would subtract it from the mean and get that value. X bar plus the error bound measure would be that. We have to calculate that. CL, our confidence level, which in this case would be 90 or 95%, is equal to 1 minus alpha. Alpha is what's left over, and that's split equally between these tails because there is symmetry here. For example, when the confidence level is 0.95 alpha is equal to 1 minus CL, which is 0.05. Alpha over 2 then would be 0.025, and we would write z of alpha over 2 is z of 0.025. The area to the right of z underscore 0.025 is 0.025. We're interested in the area to the left, and you'll see why in a minute. The area to the left of z 0.025 is 1 minus 0.025, or 0.975. Now, the reason we need this is because we're going to be using the inverse norm function on our calculator to compute that. And inverse norm only computes that z-score or k-value for a probability that is to the left of the value we want to find. Since we know the value on the right, we have to subtract from 1 to get the remaining probability here, and then use that with inverse norm. From this value, we can compute a standard normal z-score value using inverse norm of 0.975, 0, and 1 to get a value of 1.96. This can be used whenever we have a 95% confidence interval. Our z-score, z alpha over 2, will be 1.96. Here's a picture of that situation. Negative 1.96 to 1.96 would be the values if the mean was 0, which is what it is in the standard normal distribution. 0.025 are the values on the left and the right. The center portion in this case would be 95%. Now, what you're going to do next is you're going to practice this technique and find the z-scores for 75% and 90% confidence intervals. So you can stop the video for a moment, use the results that we just had to guide you, and compute the 75 and 90% confidence intervals. Okay, here's our result for 75%. When CL is 0.75, alpha is going to be 0.25, alpha over 2, 0.125. So we write z of alpha over 2 is z sub 0.125. The area to the right of z sub 0.125 is 0.125. We're interested again in the area to the left, and that's going to be 1 minus 0.125, which is 0.875. That's the value we're going to use with inverse norm to get the z-score for the probability that is to the left. We get 1.15 as a result. Now, we won't use a 75% confidence interval very often, but the 90% one will be common. So again, this z-score is one that you'll want to use, and you can follow through the procedure there as we did with this one. Step 2, calculate the error bound measure. Now this is going to be dependent on both sigma and n, as well as our z-score. The error bound formula for an unknown population mean mu, when the population standard deviation sigma is known, is given by EBM equals z of alpha over 2 multiplied by sigma over the square root of n. This should look familiar because it's related to how we worked with z-scores and k-values in the last chapter and the chapter before. Except this time we have a z-score related to our confidence interval, and because we're using a sample population, we have to divide by the square root of n. Example, from the z of alpha over 2 calculation we just did, if I give you a population standard deviation of 2, and we have a sample size of 100, then our error bound measure is 1.96 times 2 over the square root of 100, which is 0.392. Step 3, constructing the confidence interval. This is the easy part. The confidence interval is simply of the format x bar minus EBM, comma x bar plus EBM. Example, from the EBM calculation we just did, if the population standard deviation was 2 and our sample size 100, then since EBM is 0.392 from the previous calculation, we will have x bar minus 0.392, x bar plus 0.392. I didn't give you x bar in this case, so we don't have an actual computed value. The interpretation should clearly state the confidence level. So this is step 4. Explain and interpret the confidence level in the context of the problem. We're going to explain what the parameter that is being estimated, in this case the population mean, and state the confidence interval of both endpoints. So in general, our formula looks like this. We estimate with blank % confidence that the true population mean and we include the context of the problem here, is between blank and blank, and we include our appropriate units. So in the case of the example we've been following, from the 95% confidence interval we just did, x bar minus 0.392, comma x bar plus 0.392, we estimate with 95% confidence that the true population mean is between x bar minus 0.392 and x bar plus 0.392.